So today we're going to discuss computer vision, the intuition behind the computer vision, and some of the most exciting applications that have been solved using computer vision. Basically, in the past decade, or I would say 2 decades, computer vision basically has transformed and has evolved so much that it has solved several real-world, problems such as self-driving cars and object identification, classification problems. A lot of the video related or image processing related applications, they are based on computer vision and actually based on convolutional neural networks. The idea comes from the artificial neural networks, which is why we're going to talk about artificial neural networks today a little bit, not the mathematics behind it, but the intuition behind what artificial neural networks are and what is the science behind it. And then we're going to go ahead and start our discussion on convolutional neural networks. There are a few fundamentals of convolutional neural networks that we will have to understand in order to design a new application, okay, to solve a real world problem. And we will see some examples of computer vision based on convolutional neural networks. So the way I've basically divided the content for this week is to have the fundamentals understanding of artificial neural networks and convolutional neural networks, what they are today, what is the science behind that. And then on Wednesday, we will basically write a complete program to solve a real world problem, which is the image classification problem using convolutional neural networks. Something to remember in convolutional neural networks, they also need tuning. But tuning in artificial neural networks is much more difficult compared to other models because they are still considered as black box models, because we don't have a very good understanding or transparency within the convolutional neural network what goes behind the the tuning and the development of the network stuff. Just curious about image recognition, image classification. So it's image classification, and then we have object recognition, object identification. Convolutional neural networks are used for both the purposes. Image classification is slightly simpler than object recognition. There are a few other techniques that are involved to the object recognition or object identification, because even if you think from the simple, human perspective, image classification is something like this: whether or not there is something that exists in the image of some sort, like something like a human, a dog, a cat, a horse, a car, anything, if it exists within the image or not. So designing an application based on CNNs, I would say convolutional neural networks, I will call it CNNs just as a short abbreviation. That is easier compared to identifying at what locations each object of interest that you're looking for, identifying the location also. Okay, so that is a little more technical, more complicated, but there are techniques to solve that problem. Different cameras? Yeah. Recognition of white faces. So just like, so with one camera, you can do some object identification, okay? Based on some features that you identify from the image, you can do some object recognition or object identification. When you combine multiple cameras from different angles or different scenes, something like that, you can simply convert your convolutional neural network from 2D structure to a 3D structure or even multidimensional structure. It's just combining those, multiple dimensions and getting the result into a one class. So it's just extending convolutional neural network to multiple dimensions. Okay, so we will go over the examples of convolutional neural networks and image video processing in a much more detail, on Wednesday, and we will write a Python program to solve a simple problem, but we will go into a more, complicated examples of object recognition. Okay, so let's just focus on the image classification on the earlier part of the Wednesday class, and then we'll talk about the object recognition. The concepts, fundamentals that we will have to remember and understand in good detail in order for you to design a CNN for a specific problem that you're trying to solve. If you have a large, let's say, video data or large number of images to solve, a specific problem, you will need to understand multiple elements of the CNNs that actually work in a sequence in the background in order to understand or in order to predict or classify what's going on in the sequences. Something like, you want to design probably like a stop sign detection or a specific building detection. Like, out of, multiple pictures of the city, you want to identify which building is actually a federal building, a government building, a DMV building, anything, okay? So if you want to solve a problem, there will be specific elements that we will have to go over, and I will go over each of these that actually constitutes a CNN, a convolutional neural network, okay? So we will talk quite a lot about convolutional neural networks in this lecture. Once again, the slide from week 1, just wanted to show you how much we have done already and what is coming next in these 2 weeks. So if we look at this part, machine learning, we have done a lot of this already, okay? We have talked about machine learning, we have talked about symbolic learning, robotics, we have designed several search, based solutions for multiple like robotic applications or even some simulations like Pac-Man, et cetera, et cetera. We talked quite a bit about that, right? Today, we're actually going to talk about neural networks. So neural networks, if neural network does not have, multiple hidden layers, is just called a one layer perceptron, a very, shallow feed forward network. We're not going to focus too much on that because that's actually part of a machine learning course where, people learn about what a perceptron is, what are the equations behind it to, train the weights or tune the weights of a perceptron. It's just like, we will also consider, or there will be, you will see some synergy between the CSP that we have covered, like there are nodes and there are arcs. And then with each arc, there was a specific probability that was associated. We're going to talk about neural networks from that perspective also, so that it makes sense, okay? We're going to talk about deep learning. We're going to talk about like designing a neural network structure that is much deeper. We will have many layers of neurons that are going to be interconnected with each other to solve a specific problem. So we're going to talk actually about deep learning quite a bit in this week. And to solve some problems, some real world problems, very specific to image and video processing, we're going to talk about convolutional neural networks. That actually is part of computer vision. So this is what we are going to cover this week, okay? In quite a bit of detail. We will look at, remember, I think in one of the previous weeks, I mentioned that there are some convolution filters and then we just have to move them around on parts of the image and then just do some sort of identification or run some operations in order to identify something, if there is something that exists within the image. This week, we're actually going to implement that. And then for the natural language processing, next week, we're going to use recurrent neural networks to solve a specific problem for natural language processing, okay? And then we're going to be done with our course, all right? So we're going to look at basically the cognitive capabilities of, this part of AI that actually solves some problems, or the ideas behind convolutional neural networks, or even artificial neural networks that are inherited from actual neuroscience study, the study of neuroscience, decades and decades of research and studies, okay? So let's actually start with what computer vision is. The main idea behind computer vision is that you want to design an application, you want to teach the computer to identify what actually you see in the images, okay? The way we perceive the world and we basically, identify different objects by, through our eyes, we just want to make the computers do the same, okay? So identify things within the images. What we do is through our eyes, we actually perceive the world using, our eyes, our retina, then signals go through our brain, or some of the neurons fire up, and then we say, okay, if we find some sort of object with some sort of specific features, like specific, edges that we have found, or specific shape within an image, then it's probably a chair or a human or a table, et cetera, right? So we want the computer actually to do the same, to identify basically different, objects within an image that have some specific features. Okay, something like within an image or within a video frame, you want to identify, okay, if an object has some properties like this, there are two red lights, and the shape is something like this. It has 4 circular elements like components like wheels. It has 4 doors, etc., etc. So these are the specific features that you have found that you want the computer to find within an image in order to identify or recognize that it's a vehicle. You can also do this same thing, for other objects too, like a stop sign, like a human, like a road structure, etc., like a building, sky, etc. So you can perform multiple classification, okay, multi-class classification within an image. But the idea behind image processing is to find objects, find things which have specific features. So we process an image, we identify valuable features, and based on those features, we make a decision. Okay, what those features are? Those features can be specific shapes, right? Specific types of edges that you may detect within an image. And based on the combination of those, you basically make a decision. And we're going to talk about basically, how those objects are identified within an image or within a video. Before I go into the CNN and more complicated technical explanation of CNNs, we're going to start with, where did this work actually start? So back in early 2000s, like 2005, there was a technique called histogram of gradients, or it's called HOGS. This was actually one of the most famous techniques to perform image classification or object identification about almost 2 decades, 2 decades ago. But since then, CNNs, convolutional neural networks, basically have taken over, and there have been several real-world solutions to several real-world problems that have been solved using convolutional neural networks with a much more higher accuracy compared to histogram of gradients. So what is histogram of gradients? Histogram of gradients comes from the idea of edge detection. Edge detection, just detect different edges within the image. And what do we even mean by edges? How do we even detect edges? Has anyone ever heard or even applied edges, like edge detection technique? One. Okay, so actually the idea behind histogram HOGS is it comes from edge detection. What the computer sees an image is actually a bunch of pixels, right? Just that each pixel has a specific value in 3 different channels, right? Red, green, blue. As our human eyes, we can see things in 3 different channels as a combination of red, green, and blue color. There are several different colors in the world too, but our eyes are actually restricted to seeing things in only those 3 channels as a combination of red, green, and blue value. So as humans, our brains are actually trained to pick up the depth too, because the neural network, the neural network that's in human brain is actually so complicated that nobody has even ever come close to the design of a neural network that is in the human brain. Using the human brain, human brain is able to detect or identify the depths also, but there are also computational techniques to identify the depths too. Something like, light wavelength. So you get from the camera, right? From the camera sensor, you actually look at the light reflection, right? Light reflection, and then you draw an image. But for each pixel, you identify at what wavelength the light basically got reflected. So if it is too far, the wavelength of the light might vary. It might be longer or shorter. So you look at the wavelength of the light for each pixel and then identify how far or how close that object might be. So based on like the wavelength of light, you can also identify the depth. Some people do that using multiple different angles, different cameras, and then look at from the same image from different angles and then identify the length too or the depth too. There are ways to do that. Okay, let's get back to our like discussion based on just image detection based on just like a 2D right now. Okay, in a two-dimensional. So the idea behind histogram of gradients is that for each pixel, it actually looks at its neighboring pixels and how much the value of that pixel has changed around its neighbors. Okay, so what histogram of gradients does is it actually divides the image into smaller segments like this. Okay, I'm not going to draw all of it, but it looks something like this. Okay, and then it will, for each pixel, it will see how much of the direction or the value of the pixel is changing with respect to its neighbors. Something like this. So you see here, it will actually look at this area, right? So if it picks up this pixel, specifically this pixel, and then it will look at this area and see the value of the red, green, blue value of a pixel in this area was of a specific, range, like, there are some red, green, blue values for that pixel. And then it sees that how much of the value of that pixel actually changed from this area to this area. Okay, so it actually looks at the direction in which the pixel value has changed, which is why it's called the gradient. The gradient, basically the rate of change within the pixels, right? So what it does is wherever it finds out the change, the biggest change, or the change that has crossed a specific threshold that you set, it actually identifies that as an edge. Something like this. See, along this line, it actually found out that this was a huge edge because the pixel values in this area actually changed quite a lot or significantly in this region. So what it does is it looks at specific edges within each segment, okay, like this, and then it actually combines these segments together in order to identify a complete, complete shape, a complete specific shape that will then provide some sort of inference or some sort of result or outcome that, based on the combination of these edges within multiple segments, I have identified that this is some kind of shape that I'm seeing. This is once again supervised learning technique, by the way. So you actually tell the histogram of gradients that if you see specific shapes within specific segments, then it is probably like a table or a human. If you're seeing specific types of edges, right? So basically what it does is it detects all the edges within the image, okay? Then combines those segments, the larger segments within the image, and then identifies a specific shape. So, okay, before I go into the hogs examples, I want to just pose a question. Does anyone see any sort of specific shape in this image? Black and white image. Do you guys see anything, any shape, anything that you may be able to recognize in this image? Close your eyes to about like 70%. Just look at it like this. Maybe that one. Nothing? Kind of looks like what? A unicorn? Closer. Closer. Okay. How about this? Look at this. Yeah, you're almost there. Something like this.
Dr. Doom.
Wow. It looks nothing like the young, beautiful lady that we have. Okay, it's actually a picture of Lena. This is one of the most famous images that is used in the field of image processing. A picture of a, I don't know where she's from, but she's pretty. So histogram of gradients, what you do is basically based on the histogram gradient, for each pixel, you're actually seeing in which direction the value of the pixel is changing. Now you see there are quite a lot of vertical lines, right? If you look at the actual image right here, there are quite a lot of vertical lines, right? So a histogram of gradients actually will pick those changes or will pick those edges because it's looking for all sorts, possible sorts of edges or the gradients or the direction in which the pixel values are changing. And based on this information, looking at the gradient, the algorithm actually works behind in the background to perform some sort of classification. Something like this. This was actually one of the earlier works of based on histogram of gradients to actually detect different shapes within the image. If you look at the top left, so what the blue rectangles are actually the segments of those images. Within each segment, histogram of gradients actually detects specific edges, all right, identifies the edges, and then it combines all of them together to say, okay, I am seeing a continuation of some sort of specific edges within the combination of these segments. Therefore, within this combination of these segments, I identified that it's sofa. It's a sofa, all right? But the problem with histogram of gradients was that the intuition behind hogs was not strong enough, or the evidence was not strong enough that it would detect something like that in the third column, top row. It actually detected two cats facing, next to each other, sitting on a wall. Because it actually drew the shapes just like a sofa, it actually got confused and thought that it was a sofa. Okay, so what histogram of gradient also does is, you see here in this image, for example, it actually draws a segment around the tire, the handle, the pedal, like this. And then it actually combines all those segments together and then identifies that as a bicycle. Okay, yes, Rana. It's an extension oriented that then you actually are looking specifically for the orientation. If you are looking at mostly the diagonal images, like diagonal lines, or you're looking at specific horizontal lines or vertical lines, so you're actually looking at the orientations also. And based on the orientations, you want to predict or make a prediction what sort of technique, what sort of object you want to recognize. It's an extension of histogram of gradients. Okay. All right. Let's get to our main explanation or main topic, where we're gonna, basically, oh, somebody, Dr. Doom. Brendan says it was a picture of Dr. Doom. But anyway, does anyone know this guy? Geoffrey Hinton. Don't look for him on Google yet, but he actually is known as the father of deep learning. Back in the 70s and 80s, he worked a lot on the artificial neural networks based on the concepts that are inherited from the actual neuroscience research. And he made artificial neural networks practical. And he solved, many real world problems using artificial neural networks or deep neural networks. So he's actually called the father of deep learning, Geoffrey Hinton. He was, I think, either the CEO or at a very high position at Google. I think right now he's back at Stanford. I'm not sure if he is still at a very high position at Google, but he's the guy who actually made deep learning practical to solve real world problems. And I will show you some of the examples that he actually solved. So he looked at, or he studied, extensively the ideas behind the neural network, the actual human brain, what neurons are, and how they look like and what are their components within the human brain. So there are three major components of a neuron within the human brain that are actually inherited in order to design an artificial neuron. Okay, something like this, that a human neuron basically has a nucleus. Okay, it has several dendrites. Okay, several dendrites are actually the input. They receive the input from other neurons. So you see there are quite a lot of branches that are shown. These are actually the inputs to that specific neuron that are received. Those inputs are received from the outputs of other neurons that you have within the brain. Does anyone know how many? So it's not the accurate estimate that how many neurons there may exist in the human brain. Have you ever 40 million? 1/3, you said. It's about, so there are about an estimated number of neurons is about 120 billion neurons within the human brain, but that's not like, it's not the accurate estimate, it's just the estimate. There might be way more number of neurons within the human brain, or maybe less. But you can just think that there are 120 billion neurons within the human brain that can give you an idea of how complex the machinery there is within the human brain, which is why it's just said that the human brain is the most powerful and smartest thing, in the universe that has ever been observed. Okay, so there is a bunch, billions of neurons like this that actually sit in the human brain and actually help us make a decision. It has a nucleus, it has dendrites, basically input, all right, and then it has an output, an axon. Okay, so the way these are connected with other neurons are called synapses. Okay, are called synapses. These. So you see, then these are actually then connected with other neurons within the human brain, and together they make about 120, billion neurons. So the three most important things: nucleus, dendrites, the input, and the axon, the output, axon terminal. Okay, so based on that idea, we actually, Geoffrey Hinton was one of the main guys to actually design artificial networks. So these neurons help us make a decision or identify something within the image. So what we do, axon and dendrites. Okay, dendrites, these are the inputs. These are the three most important, elements in terms of, so the artificial neural network is not exactly the same as the human brain is, but there are some features, some properties that are inherited from the human brain. So these are the three most important features that are inherited from human brain. Okay, so we will see that very soon. How do these neurons basically help us make decisions? They actually basically fire up. Whenever we provide our neurons some sort of input, they fire, they blink, okay? And some specific, the way our neurons or neural network is trained, whenever we see something or we provided some sort of input, some of the neurons fire up, and then basically they help us identify, oh, okay, we actually, we have identified something within them. What can be the input in terms of the human brain? What can we consider as an input? The input is, basically what we smell, what we see, what we touch, right? So these are all what we eat, okay? So these are all the inputs that humans basically can receive, and then the human neurons process that input, and then some, a set of neurons actually fire up and help us make a decision. Something like this within an image. If I see, a specific shape like a chair, it has horizontal and vertical edges. So we see those specific edges within the human brain. The input goes to the neurons, and some neurons that are actually trained, they fire up and they help us identify that this is a chair, because this is the way our brains are trained. This is why, like, when you show something to a child that has never seen a specific, object before, they will not be able to know what it is. So there has to be specific, like some sufficient number of input samples that you have to provide in order to train the neuron. This is actually the human brain looks like. This was taken I don't know when it was, 2020. Okay. So this is an actual image of a human brain, just a portion of a human brain. That's how neurons look like. Okay, neurons look like, and this is basically the neuroscientific interpretation of a human brain. Before this, by the way, this is actually part of the back of the brain is called cerebellum. Okay, so this is actually an actual image, microscopic image of a cerebellum, a human brain. That's how it looked like. Before this, the human brain actually was drawn to be something like this. So this was this gentleman who made this discovery, or this guy's name was Santiago Ramon. Sorry, Cajal. Okay, thanks for correcting. So this guy basically back in 1895 or 1897, something like that, that year, he was actually looking at the human brain in a microscope. And he basically, while he was looking at the brain, what he saw, he actually drew. He drew a picture of that, and he thought that a human brain basically looks like something like this. Okay, so he drew that, and then he patented. And this is basically, the idea behind the human brain, what he saw, okay, and he just drew what he believed to see. Right. Not sure if that was patented at that time, but it was copyrighted. I think so. You can check it. You can check it online. I'm not sure. Okay, I don't exactly remember. But this guy basically made this, possible to actually see the human brain. But now techniques these days are much more sophisticated to see the human brain in much more detail. Okay, let me just show you what actually works behind a human neuron. How human neuron works. Remember three things, right? The input, dendrites, the neuron's nucleus itself, and then the output, right? The axon. So suppose that this is the nucleus of neuron that we have, all right? We have a bunch of input, right? Input independent variables, variable 1, variable 2, et cetera, et cetera. Just recall our previous lecture where we looked at the data, right? Where we had the age and then expected salary, and then we had purchased or not purchased, like right, the target outcome that we have. All right, so we have X1 and we have X2. Whose pen is this? The squeaky pen. Oh, I see. Okay, it sounds like there is a bird. There's a sparrow. Okay. So we have a bunch of input, right? X1, X2, Xn. These are all independent. Just like we had the age and the salary as an input variable, right? These input are provided to the neuron, all right? The neuron does some sort of processing and then produces an output. Okay, that actually makes the prediction. So here, this might be your purchased or not purchased. So what human brain does is it actually has these dendrites, all right, the synapses, the connections, and it actually tunes or adjusts the weight in some way that you provided the data based on the data that the artificial neural network has. It actually trains these weights and then says that if I see a specific type of input, I'm going to fire up. Otherwise, I'm not going to fire up. Something like this, like, for not purchased, all right, this neuron might not fire up. And for purchased, like if somebody sees that, okay, if somebody's salary is $110,000 and they are, let's say, 27 years old, okay, those inputs it is providing, and then neuron does some processing here, okay, to produce an output, and it will say, oh, I have seen the salary and the age for a specific value or within a specific range that is higher than the threshold that I should have thought of. Therefore, I'm going to fire up and I'm going to propose and predict that the person with these input variables basically are going to purchase. So this neuron actually fires up based on the input. So this neuron actually does something, right? Right in here, in the nucleus, there is some sort of processing that goes behind. It actually is very, very simple. So suppose that we have a bunch of input variables, right? Then we have an output variable, right? Or target outcome. We may have multiple outcomes. For a binary classification, we can only have just one outcome, right? Either 1 or 0. If we have multiple classes, you can have multiple outputs. Something like this. Suppose that you solve another problem that we are going to solve, by the way, on Wednesday, is that suppose that we want to predict if within an image, did we see a dog? Did we see a cat? Did we see a human? Did we see a table? And so on and so forth. We can have multiple outputs too. But just for the understanding, let's go with the one output. What happens within the neuron itself? Okay, so we have a single observation, and this should be single output. What happens is the neuron basically gets these weights trained based on the input samples. How do those weights are trained? Those are actually trained using back propagation algorithm. I'm not sure how many of you have worked or actually designed a back propagation algorithm in machine learning. I'm pretty sure that you guys may have. No? Did you guys go over artificial neural networks? Oh, no. Not neural networks? Okay. All right. It's okay. So there is an algorithm called back propagation algorithm. What we do is we look at the error. So what might be the error here? Basically, the y, the actual y minus y hat. Remember y hat, the prediction. We look at the squared error for all the samples. We get its first order derivative, and then we back propagate that error to the, all the way to the back, and then we adjust the weights based on like W1 equals W1 plus this is the learning rate, and then that specific derivative that we have. So the weights basically get adjusted based on the input. I'm not going to go over into too much detail about back propagation here because it's not going to be a machine learning, class. All right. So I said that the neuron basically needs to have some sort of processing. Well, all what this neuron, each neuron does is, if you open this equation, it actually gets to a multiple linear regression. If you guys remember from the previous class, where we had, remember, m1x1 plus m2x2 all the way to mnxn, right? So we actually fit these slopes based on and have these input variables, and we simply have a multiple linear regression. If you open this equation, it actually is the same as, you see, w1 x1 plus w2 x2 all the way to wn xn plus the bias factor, beta or b. So it actually is a very simple multiple linear regression that the neuron gets trained on, and it actually adjusts its weight. Another thing is, so now we have actually the multiple linear regression of all the input variables. We have adjusted the weights. How should the neuron blink, or how should the neuron fire up? So next step is, so in the first step, it actually gets this sum, xi, I of 1 up to n. What's the n? N is the number of samples that you have within the data. Remember, we have the 400 samples within the data from the previous class, right? So for all of those, basically it gets the summation, and then it performs another operation that is called activation. Activation is actually the one that helps it fire up. Or when I say the neuron fires, that means the neuron activates or not activates. Okay, it blinks. It's either 0 or 1, right? If it's 0, it doesn't activate. If it is 1, it activates. It just works like that. There are two things that are actually going on within this neuron. All right. So what do we have to activate? How do we help the neuron activate? okay, for different types of problems. This is actually very important so that you understand what sort of activation function would you need to apply based on the specific problem that you're trying to solve. Okay, there are some activation functions that we have that we will go over in a very brief detail. Okay, suppose that you have just binary classification, right? Either 0 or 1. That means you might be okay with a very simple activation function. Very simple. What you do is, that's called the threshold function. So on the x-axis, you have this phi value. Phi basically is this sum to n wi xi that goes from 0 to some value, based on the domain that you have selected. And then you say that it should fire up if this sum is greater than or less, greater than or equal to or less than something, some threshold that you have. And in this threshold, in this like binary classification, if you're just only doing binary classification, that means you're just either having 0 or 1, right? You're just having either 0 or 1. So you say that this thing, your activation function will be 1 if this phi value is greater than 1, and it will be 0 otherwise. Something like this. So you see, if this phi value is 0, it will be all the way to 0. As soon as this phi value becomes greater than 1, greater than 0, your activation will be 1. It will activate. Its value will just become 1. So this threshold is simply an if condition that is behind this activation function. Okay, so we have 1 threshold. This is actually pretty helpful when you do a binary classification. Okay, this is very helpful if you do a binary classification. So suppose that you have a cat or a dog classification, or purchased or not purchased, something like that. For that, threshold basically function works pretty well. Now suppose that based on like limited lack of data or insufficient data, you are unable to do the classification with 100% probability. What happens? Something like this, sometimes some kind of deja vu, situation that we have. Sometimes you may have noticed that, that you might be sitting and then all of a sudden you think that there is a cat or dog just like ran in the background or something. And then all of a sudden, then you just take a look and say that it was actually a ball moving or something. Sometimes it happens, right? Like as you're sitting and all of a sudden you may have thought that there's a bird who just flew, that is what happens when your brain doesn't get sufficient information, when there is a lack of information. In that case, what your brain does is actually a probabilistic classification. Your brain says that, I'm not 100% sure. It might have been a bird. It might have been a dog. It might have been a cat running around. But then when you look at it, you see that there is a ball. There's a ball or there is something else. That's when you get sufficient information. In those scenarios, you can also perform classification, a probabilistic classification. Okay, something like this. You say that, all right, I am actually 80% sure that I saw a dog in the image, and I am 20% sure that I saw a cat in the image. There is an activation function for that purpose too. That is simply an extension. I'm not going to draw it here. I'm going to draw it right over here. That is simply an extension of threshold function. All what it does is it takes the threshold function and it simply smoothens it. It has a smooth version of threshold function. How do we, what do I even mean by smooth version of threshold function? Something like this. So before the threshold function looked like this, now it will look something like this. Just something like this. Because now you can have a probabilistic classification instead of just 0 or 1. And it's called, so this is basically the 0, phi value. Phi is this, okay? Phi value. So this function, the equation behind this function is 1 over 1 plus e to the power minus phi. Minus phi is actually that summation. So we calculate the summation and we take e to the power minus that summation, that phi value. That's called the sigmoid function. Sigmoid. Okay. There is one more that is the most famous activation function that is used in convolutional neural networks. And that's called the rectifier linear unit, ReLU, rectifier function. What does the rectifier function say? Rectifier function says that as a value of phi, like this, all what you do is pick up the maximum between 0 and phi. That is it. Very, very simple. Until the value of phi is 0, the activation is going to be all the way 0. And as soon as the phi value becomes, starts getting larger than 0, it will pick up the maximum, which is going to be phi. It looks something like this. So for all the way up to 0 value of phi, it will be 0, and then slowly it will start jumping, it will start spiking. Not spiking, but it will have a smooth kind of rise, because we're just simply using this max function. Make sense? Does it make sense? Because all what we're doing is we're just looking at these values, the phi, the summation. Summation, until it is 0, the activation is going to be 0. It's not going to fire up. As soon as we have the value of phi higher, then we're going to basically have selected the value of phi instead of 0. And you can set a threshold. Say, if it goes beyond, let's say, 50% value of phi, if it goes beyond 5 or 2, 3, whatever, based on your problem, just fire it up. Okay, so we'll talk about those quite a bit. These rectifier is called the rectifier function. Yeah, but this is actually extremely important in images, which is why it's used in image processing quite a lot, or convolutional neural networks, because you see quite a lot of non-linear when you process the images. You actually see quite a lot of non-linear edges within the images. This is actually very good with non-linear trends. It preserves the non-linear relationship of pixels with each other so that it represents the non-linear relationships pretty well compared to other functions, activation functions, which is why this is one of the most famous, because it preserves the non-linear relationships. I have a slide on that will explain why rectifier linear unit is actually pretty good. Okay, all right. Let's just go over one more example, and then I promise we will go over the convolutional neural networks, what convolutional neural networks are. So before we just looked at one neuron, right? You can have several neurons within your neural network. This is only just one layer. It's just one layer. It's not called the deep neural network because there are not multiple layers. This is not how human brain is. So that's called just one feed-forward neural network. You have multiple independent variables. Their weights are actually trained on here. The neuron performs that to the summation, the summation, and then the activation. And whichever neurons are activated, we're going to have our decision or the classification, whatever problem that we're trying to solve. What you can do is, let's say for this neuron, you can implement a rectifier linear function. For this neuron, for all these neurons, you can implement rectifier linear unit. And if you have a probabilistic classification problem, at the end, you can actually implement a sigmoid function. So you can use a combination of these. So this is very, very important for you to decide to identify what sort of problem that you're trying to solve. Is it a multi-class classification? Is it highly nonlinear, which is why you need to have data visualization, et cetera, et cetera. If it is just linear, then what sort of activation functions are you going to implement to have your network with the highest possible accuracy? And then if it is just simply a binary classification, just use a threshold function. Otherwise, if it is a probabilistic classification or a highly nonlinear or multi-class classification, you can use a sigmoid function. So you can use a combination of those. All right, but tuning the weights of these parameters has still to date has been an issue because it's a black box. It's called a black box model. One more thing is why are the neural networks considered to be one of the most powerful machine learning approaches in order to solve real world problems? Still today, it's still considered to be one of the most powerful techniques. And why? What is the reason? Not many people will explain this to you. This is something very important for you to understand. Actually, within the neural network, each neuron gets trained on a specific type of input. It looks at specific types of inputs, and then it gets trained to make a specific decision, to make a part of specific decision within your network, and then together, combined with tens or hundreds of different neurons, it actually can perform very highly complicated, analysis also. So far, the most, I think, complicated or the most complex neural network that has been designed by Google, it has 1.7 billion parameters. 1.7 billion parameters. What are those parameters? Actually, 1.7 billion connections that they have. All right, really quite large, very big network, which is why they have the most comprehensive or the most accurate neural network model that has been designed so far that actually won a competition from a human being too. Something like this. Suppose that in an image from a very far distance, you saw two horses standing. They actually look so small that your human brain might get confused and say, they might be horses or they might be dogs or donkeys or something else. Your human brain might get confused because of the shape or the size of those horses within the vision that you see. Neural network designed by Google actually has performed classification better than the human being in those scenarios. So that is the most complicated. I'll tell you why this is important. Now, suppose that this is a very, simple kind of classification that you have, whether or not you want to purchase the house. Okay, a few months ago, about 7 months ago, 8 months ago, I bought a house, right? So there are specific things that you have to take care about, like, based on your preference, you might want to buy a house with some sort of preference, something like this. How old is the house, right? How many bedrooms are you looking for? How far is it from the city, from the downtown, from the city, right? What is the area in terms of the square feet, right? So you might be looking at these sort of, input variables or some factors of interest that you might be interested in, right? Something like, for young people, basically they are much more interested in buying a newer house compared to an old, house built back in 1930s or 40s. Some, like young people might be interested in buying much more newer houses. People with, with families, with kids, they might be looking for what are the number of bedrooms that they have, right? So these are different, interests or factors that you might be interested in. Each neuron gets trained, something like this. So this neuron is specifically looking at how old the house is and what's the area, how big the area is. So then it actually trains, maybe it gives the 0 weight here, some sort of weights like that, something like that, okay? This neuron might be looking at the distance, the age of the house, and how many bedrooms is a person looking for, okay? Then another neuron might only be looking at just the, let's say, distance to city. So each neuron looks at the specific combination of the input variables and then fires out, which is why it can perform highly non-linear tasks too. So each neuron has a specific purpose, which is unlike many, many other machine learning techniques.
Is that purpose merge over? Somehow.
Initially, they're just randomly set up. So if they all get trained on the same input, same columns, what these neurons can see specific patterns in the data. Like there are some samples, like out of those, let's remember we had 400 samples, right? Age and salary. What each neuron will see is that it will actually look at specific rows or specific samples within the data and says that based on this, I'm going to set my weights higher for specific samples, specific rows. And because the weights for those specific rows is higher, whenever I'm going to see those sorts of input, I'm going to fire up. While for the other neuron, it will say, I'm going to actually provide less weight to those specific samples. So it actually based on different samples or different rows, each neuron has a specific purpose. They are not going to get trained basically exactly the same way, each of those. It is the intuition behind artificial neural networks that each neuron looks at specific samples and provides higher weight or lower weight to specific samples. So neurons in different layers, they do communicate with each other. For here, each neuron, or just only one layer, each neuron communicates with every single input. But right now, I haven't put a second layer, something like this. If I have a second layer here, then each neuron in the next layer will communicate with the neurons in the next layer. Okay, it will actually get an input from the previous layers and then perform the activation. I have a demonstration of the models. I'm gonna show from here. How do I bring that? I'll open this website quickly. Copy link, and I'm gonna move this over to show you how Google TensorFlow has made this library available as open source. How do I? So this is an actual open source library that was designed by TensorFlow. This is also open source, by the way. There is a GitHub link that is given somewhere in the, in this article that implements artificial neural networks to perform, some, classification problems or some regression problems. Just like how, remember we did the classification problem in the previous class. So you can implement, more neurons, less neurons. You can play with this demo and perform, let's say, the classification. If I say for this, I'm going to I have two inputs like X1 and X2, X1 and X2. I'm going to have only two neurons in the middle in the layer, and I'm going to have only one neuron as an output. So I have two hidden layers. Maybe I'm going to have two neurons in the two hidden layers. I'm going to perform basically, let's say, I'm not going to type 5 because I'm in a tablet mode. All right. Oh, it was automatic. So by the way, what we do is we provide X1 and X2 input values, these data points, all right? And then these neurons basically are getting trained to perform this, classification, to distinguish between these two classes. You can have more neurons, just like this, okay? And then you can perform, you see slowly the loss, the error rate gets lower and lower, and it is able to perform such a good, classification. Just a simple linear, discriminant analysis. It has examples, other examples too. Where is that? Regression. What is that? Okay. Oh, it still performs the classification. Oh, activation function. There's a tangent edge function. So you can perform rectifier function, sigmoid, linear, etc., etc. I think there were some other examples given to data. I thought that there were other examples here too to perform more complicated regression or classification. But size, ratio, where did it go? Just, oh, this is the test data, by the way, train test split. But I think, yeah, so there were other examples, demonstration, but I can't find it. But I think I've already provided the link to this website. You can even download this library and perform a classification or regression task based on completely your own data. Okay, so they have made this open source library, which is actually very impressive as a web application. Let me go over just 2-3 more slides, and then I'll be done. All right. Can you keep looking at this face and just identify where her eyes and mouth are? Doesn't that start like hurting your brain when you keep looking at, like, you want to see where her eyes are and where her mouth is, right? So, and then if you look at this, how many of you think that this guy is looking towards this direction, towards his right? Or how many of you think that it's looking just front? The guy is looking towards you. If you look at these features, then you will probably think that this guy is looking towards this direction. But if you actually look at these, you probably think that this guy is looking towards you, right? So that are actually the way our human brains are trained, are actually looking at some features. Some features, the way our human brains are trained, we have never seen this face before, right? With 4 eyes and two mouths, right? This is why our neurons get confused. They fire up in a way that has never been done before, which is why your brain starts hurting and your brain starts getting confused, because you have never seen these sorts of trends, these sorts of edges. So that what we are looking at in convolutional neural networks, we are looking at a combination of edges, combination of shapes, or combination of features, and we actually train our convolutional neural network to identify some sort of shapes or some sort of objects with some features. So these features are going to be the most important element in our convolutional neural networks. This is actually one of the classification problem that Geoffrey Hinton did back in late 1970s or early 80s to perform basically some sort of classification. Something like this. You see, with the cheetah, it was about 90%. His deep convolutional neural network was able to identify the cheetah based on the features. Certain features in the image was able to identify the cheetah. Then looking at the bullet train, well, pretty good classification. Here, what do you guys think this is? A hand glass, right? Magnifying glass. What the model did in that case was it thought that it's a scissors. Why? Because there was not sufficient data that was provided. The amount of information was not basically sufficient. The idea behind convolutional neural networks is you provided an image, the convolutional neural network performs a sequence of multiple steps, all right, and then performs the segmentation. It segments different areas within the image and names them, like car, trees. I don't know. You're not able to see these labels that I have. Like this is road. This is the moving car. Like greenery or trees, etc., etc. What it does is convolutional neural network. All what it does is it sees this image as just a bunch of pixels in 3 different channels: red, green, blue. When you process an image in a color mode, you are looking at the image in 3 different channels: red channel, green channel, blue channel. And then you have the dimensions of the image, right? Like suppose that your image might be 512 by 512 pixels, right? A square image. So all what it does is the computer actually looks at a bunch of, the image, it treats that image as a bunch of pixels. Something like this. Suppose that as a human, when we look at the space, we actually see things like this. Something like this, like, there is a face and then there are eyes and we can see that. What the computer does is it actually looks at the image as a bunch of pixels with values. Like everything is 0, well, 0, 0, 0, 0 for the red, green, blue channel is black. And then 255, 255, and 255 is all white. And then all those combinations in between make different colors that we can see. Gray is 127, 127, 127. Okay. So what the computer does is it looks at a bunch of, it looks at the image as a bunch of pixels with values. So you see something like this here. So all of them are just 0 or all of them are just 1. And then where the face is, they have different values. Now the convolutional neural network's job is to identify these edges or these features and remember those and apply those techniques based on multiple different types of features. How does it do that? Please remember this because this is very important sequence. What it does is it performs a convolution of. Remember, I say that you take a small portion of the image or a filter, you run it on the portions of the image and see what sort of edges you are detecting within the image. Is it a horizontal edge? It is a vertical edge? Is it a diagonal edge? Is it a curved edge? Is it a circle? Is it an ellipse? All sorts of edges. It identifies those types of edges using the convolution operation. I'll explain what convolution operation is on Wednesday before we start coding. Then it does pooling to reduce the size of the image so that at the end of the neural network, we have small enough input so that we can perform inference in real time. Because suppose that if we have 1,000 by 1,000 image, so we have 1,000 by 1,000 image, you have 1 million input variables. Because each pixel is going to be your input variable, independent variable, 1 million. For 1 million, you're going to have a deep enough neural network to perform the classification. Pooling helps reduce the size of the image. So at the end, when it goes to the output layer, there are only about 150 input variables left, which are the most prominent features. Then we do the flattening. All what we do at the end is we have a 2D matrix, we just flatten it into a 1D array, one-dimensional array, and then we perform the full connection. We have the artificial neural network at the end. That's what it is called, convolutional neural network. What we do is, as an input variable, we provide it as an image. We perform convolution operations, pooling, and then flattening. Based on that, we then provide it to an actual deep artificial neural network to perform the class. And we will go over that on Wednesday in much more detail. We will have a classification problem, which is going to be something like this. And we will implement each of these steps on Wednesday as a program. So this is a pictorial view of what we are going to code. In the beginning, we're going to have a set of images. We're going to perform several convolution operations, pooling operations, and then we're going to design a deep neural network at the end to help us identify what sort of objects we are looking at in the image. This is why. So you see, deep neural network or artificial neural network doesn't have this part. It only has this part. When we say convolutional neural network, we have all these convolutions and pooling operations in the beginning, and then we pass it to the deep neural network and the flattening layer. So on Wednesday, please attend. I'm going to send some announcements so that everybody attends, because we're going to write a program for a very cool, image classification and object identification problem. Sounds good? All right, we're done. We're 5 minutes over.